Let's analyze a classic system design failure. So let's say you had one requirement to send 1 million emails every morning and you built a scheduler and it starts running and then the server crashes. The immediate outcome is chaos, right? Some users would receive the email and some did not. And this wasn't just a server crash, it was probably a design failure, right? So let's think about the root causes. Firstly, a monolithic design is an issue here. The process that determined when to send the emails was the same process that actually sent them. And this created a single point of failure where the entire system state was concentrated in one volatile process, right? Second, the operations were not idempotent, right? There was no mechanism to safely rerun the process, right? A simple restart would guarantee duplicates, right? So it would really corrupt the user experience side of things, right? And third, explicit state management, right? The progress of the entire operation was stored in the memory of that single running process, and when it crashed, that state was lost, leaving you with no really verifiable work of what had been completed, right? So you did not really know what emails had been sent, etc., etc., right? This architecture was fundamentally brittle, right? And it was never a question of if it would ever fail. It would eventually. So how do we re-architect this for a high throughput and resilience, right? So we address each of the three flaws that we talked about, right? First, to solve the replay problem, we mandate idempotency at the worker level. So every send email function must be designed to be safely rerunnable. And you can achieve this by using an idempotency key. For instance, you can use a composite of the user ID and the date, right? So before executing, the worker performs an atomic check and set on this key in the store, right? Persistent store. If the key is already present, you would skip sending the emails again, right? Next, to eliminate the single point of failure, we decouple the system component with a messaging bus. So the scheduler is now refactored into a simple producer, and its only job is to generate millions of whatever emails and place them onto a durable queue like a Kafka or RabbitMQ, right? So the email sending logic now lives in a fleet of identical stateless consumers, right? And this allows us to scale the workers independently and ensure that if one worker crashes, the job message simply becomes visible again and another worker service could process it, right? Finally, we address the state ambiguity by externalizing and explicitly managing the state, right? How do we do it? So a job is no longer just running. It's a finite state machine. Queued, processing, completed, failed, right? And when a consumer pulls a message, it must really first acquire the log, right, on the jobs ID and perhaps using Redis, right? So it sets the state to processing, and then once successful completion is done, it releases the log and sets the state back to completed, right? So this distributed log prevents race conditions and ensures that even in the case of a crash and two workers cannot kind of really reprocess the same message, right? So basically, by replacing the monolithic with idempotent workers and decoupling messaging bus and explicitly distributed state management, you can transform a fragile scheduler into a resilient, observable, and a horizontally scalable system, right? And this is really the foundation of reliable distributed task execution. If you learned something new, hit that like button, subscribe, and let me know if you have ever faced such a job scheduler and you had to re-architect or redesign it. Cool, thanks for watching.